Good morning, everyone. This lesson that we're going to do today is from the textbook. This is 5.2, Properties of Rational Exponents and Radicals. Okay, so one of the reasons why we did all those lessons prior to entering into the textbook is because your book just kind of jumps right into it. Basically, these are all the properties that we studied previously with some examples showing you how they would work with numerical values as opposed to variables, but we've discussed all of this already, so we're just going to jump right into it. All right, so it says use the properties of rational exponents to simplify each expression. So for this first one, we're going to add because the bases are the same. So 1/4 plus 1/2. We need to get common denominators, so that's going to be 2/4 instead. So 7 to the 3/4 power is your final answer. We won't write it in radical form, but just to review, it would be the 4th root of 7 cubed. Okay, B. Now this one, we're doing power to a power. So when I bring this exponent in, it becomes 6 to the first power, which is just 6, times 4 to the 2/3 power, and we're just going to leave our answer like that. If you wanted to separate it with a parentheses instead of the multiplication symbol, that's fine too. Okay? All right, C. One of these are pretty straightforward. Bring the power in, so that becomes 4 to the negative first times 3 to the negative first, which is just 1 over 4 times 3, which is 1/12. Here we have to subtract, so 5 to the power of 1 minus 1/3 gives us 5 to the 2/3. Here, bring the powers in, so it's going to become 42 over 6 to the 2/3 power. And then, oh, sorry, I didn't bring the power in. I pulled the 1/3 out because then I can simplify 42 divided by 6 and get 7 to the 2/3 power. If I was to bring it in, I could still get the same answer. It would just take an extra step. Okay, example 2. Now we're using the properties of radicals to simplify each expression. So a couple things I could do here is I could put them together, like put 12 and 18 underneath the same cube root. And now what I'm thinking about is I want numbers cubed or perfect cubes. You can think about it either way. I think when you're working with larger numbers, it's easier to think about perfect cubes. So for me, what I would do is I know that 12 is 6 times 2. I know that 18 is 3 times 6. And then if I combine these, I know that's 6. So I have the cube root of 6 cubed, which is just 6, okay? If you wanted to find perfect cubes, it's a little bit harder because I know 8 is a perfect cube, but that doesn't end up being in here. So I feel like breaking it apart is actually easier in this case. You could multiply 12 and 18 if you wanted, but I feel like it's not as efficient and get the cube root of 216, but I don't think any of you know that 6 times itself 3 times is 216. So I think this way is much more efficient and straightforward. Okay, here. We want to simplify this expression, and what we're using is the fact that you can pull apart radicals or you could put them together depending on what's going to help you simplify the expression. So in this case, they're already pulled apart. What's going to help is to put them together because now I can divide 80 by 5 and get 16, and then the 4th root of 16 is just 2. So a lot of problems in this lesson, or maybe about half of them, will be using the rule in the opposite way. Okay, some new information, some that you might already know. If you want an expression involving a radical with index n, meaning a radical with a cube root or 4th root or 5th root, the index is referring to the root. If you want it to be in its simplest form, then these 3 conditions have to be met. Okay, the first is that no radicands have perfect nth powers as a factor other than 1. So what that means is if you're taking square roots, Let me give you an example. If you're taking the square root of a number, you have to pull out all perfect squares. If you're doing the cube root of a number, you have to pull out all perfect cubes and so on. If you're doing the fourth root of a number, you have to take out quantities that are being raised to the power of 4. So that's what that means. Basically, just simplify what's under the radical if possible. The second is that no radicands or no radicals, radicans is another way of saying radicals, contain fractions. And this kind of ties in with this last one, okay? You can't have a fraction in the denominator. That's the main thing, the main takeaway from the second and the third bullet point, okay? So as long as all of these conditions are met, your radical is in simplest form. All right, so let's look at each case. Here, in example 3, I want to simplify this. Make sure that it's in its simplest form. Now, there's no fraction, so I'm not worrying about the second or the third component of what we just read. What I'm looking for is, are there any perfect cubes? Because we're taking the third root or the cube root. Any numbers that are being raised to the third power, in other words, okay? Now, I don't know any perfect cubes contained inside of 135, but I do know that if I break apart 135, I'll eventually find a perfect cubed or a number cubed. So what would go into 135 evenly? Well, 5. So I would do 5 goes into that 2 7 times, and there's my perfect cube. So the cube root of 27 times the cube root of 5, if you want to break it up. Some people skip this step. Cube root of 27 is 3 because 27 is 3 cubed. And then the cube root of 5 we just leave under the radical because that does not contain any perfect cubes. And that would be your final answer. Okay, for B, in this case, I have a fraction with radicals, so I need to, what we call, it's written right here. So I need to rationalize the denominator, okay? When we have radicals in the denominator, this is what we do. We need to rationalize the denominator. In other words, what that means is I want to multiply the top and bottom of this fraction by a value that gets rid of the radical in the denominator but keeps the expression equivalent to what we had originally, okay? So just to make sense of that, let me show you what the value of that fraction actually is. It's a little bit harder on this guy, but we're just going to do it. Okay, so if I do 7, I probably need more parentheses, hold on. If I do 7 to the 1/5 power, which is the same as taking the 5th root of 7, and I divide that by 8 to the 1/5 power. Okay, hopefully I did that right. That is approximately 0.97, okay? All right, now I need to get a radical out of the denominator, which means I need perfect 5th root. I don't know how you say it actually. It's perfect squares, perfect cubes, and then perfect, I don't know. If any of you know, or if any of you want to look it up, feel free to do so. But I don't know what it's called. I would just say a number to the 5th power. That's what I need to get rid of the radical in the denominator. So there's 2 ways you could do it. Now, I have 1/8 in the denominator. So if I wanted to get a number raised to the power of 5, I could just multiply top and bottom by 8 to the 4th. Okay? Now, 2 things that I want to say here. Why am I choosing to multiply by the 5th root of 8 to the 4th? Because if I combine these two, under one radical, I get the 5th root of 8 to the 5th, which would just be 8. So I remove the radical from the denominator, okay? The second thing that I want to say is that the reason why I'm allowed to do this is because any quantity divided by itself is just 1. So essentially, all I'm doing here is multiplying this fraction by 1. That's all I'm doing, okay? So I'm not going to change the value. It's still going to have the same value. So this is one way to do this problem. I don't think it's the easiest way, so I'm going to show you another way. I can take 8 and rewrite it as 2 cubed. Why? Because 2 cubed is 8. So now I have I have 3 2's in the denominator. How many more would I need to get a power of 5? I would need 2 more. So I'm going to choose to multiply this fraction by the 5th root of 2 squared, okay? Why? Because it's just better to work with smaller numbers. 8 to the 4th, some ridiculously large number, and I just rather wouldn't. So now what I have is the 5th root in the numerator of 7 times 2 squared. I'm going to combine, or I just combined those two because they both have the same root, the same 5th root. And in the denominator, what I have is the 5th root of 2 to the 5th power, right, using exponent rules. 2 to the 5th power is 32. The 5th root of 32 is 2. Or I could just think about the fact that these cancel each other, negate each other. So what I have is the 5th root of 7 times 4 is 28 over 2. Okay, let's go back to the calculator. So the 5th root of 28 divided by 2. The 5th, oh wait, I'm writing it wrong. 28 to the 1/5 power, which is the same as taking the 5th root divided by 2. And what do you know? We get the same thing. So all I'm doing is rewriting the first expression in an equivalent form with no radical in the denominator. And what we call that is rationalizing the denominator. Okay, so on any test or quiz, you cannot have a radical in the denominator. You would have to rationalize the denominator to get full credit. All right, moving on. For a denominator that is a sum or difference involving square roots, multiply both the numerator and denominator by the conjugate of the denominator. The expressions a root b plus c root d and a root b minus c root d are conjugates of each other. Okay? Conjugates are kind of, you could think of it as like opposites of each other. You would use this method to rationalize the denominator when you have more than one term in the denominator. Okay, so this you use to rationalize the denominator. Hopefully I have space. When there's more than one term in the denominator. I'm running out of space. Okay. All right. Okay, so I'm going to come back to this part. Let's just begin. Example 4. So I have to rationalize the denominator because there's a radical 3 in the denominator, and I can't have that based on what we read up here. So I'm going to rationalize it. Now, because there's 2 terms in the denominator, I need to multiply by the conjugate. Okay, it's not enough. Since this is the square root, I would need a perfect square. It's not enough to multiply top and bottom by root 3, because when I distribute, I'm going to still have 5 root 3 in the denominator. So that just doesn't work, okay? So what you have to do is multiply by the conjugate. Now, the conjugate, like we saw up here, is just the opposite. It's literally the same thing, but opposite signs. So what I need to do is I need to multiply the top and bottom of this by 5 minus root 3. So literally the same expression, just opposite sign. Again, any quantity divided by itself is just 1. So all I'm doing here is multiplying 1 over 5 root 3 by 1. Okay? All right, so now we just multiply this out. It's not too bad. You do 5 minus root 3 times 1, which is just 5 minus root 3. Here, we have to FOIL, but remember, whenever we're doing conjugates, we don't have to do every part of FOIL. And I don't particularly like FOIL, but I know that a lot of you do, so that's why I'm using this. Anyways, for FOIL, we do first, outer, inner, last. But because I'm multiplying by the conjugate, I only have to do first and last because the outer and inner components will always cancel out. Okay, so first, 5 times 5, 25. Last, root 3 times negative root 3 is negative root 9, or just 3. And now I just simplify a little bit further, and there we are. That is the simplified version of 1 over 5 plus root 3. Okay. Now, this part up here. This comes into play when we look at example 5, so that's why I'm going to address it now. Radical expressions with the same index. Again, the index is the root, and radicand are like radicals. So to add or subtract like radicals, we just use the distributive property, which I don't really think about it as using the distributive property, but that's what you're doing, okay? Same index just means same root, and radicand meaning number under the radical. Okay, let's look at example 4. They said distributive property. I like to just think about it in terms of, I guess, like what it means to multiply, which we talked about at the very beginning. Multiplication comes from repeated addition. So what does that mean? You don't have to write this, but I want you to understand it. I have 1/4 root of 10. Here, what does that mean? It means I have 7/4 roots of 10. In other words, I have 4 root 10. I'm just breaking apart this. So I have 4 root 10 plus 4 root 10 plus 4 root 10, 4 root 10. How many times? 7. That's a 7 times. That's what this means. So in total, what do I have? What's the simplest way to combine this? If I have 7 here and I have 1 here, I have 8 and 4 root 10. I have 8/4 roots of 10, okay? So you can think of it as combining like terms. In order to combine them, they have to have the same root and the same radicand, the same value under the radical, okay? If they don't, you can't combine them. All right, not only could I apply this with radicals, but I could apply it with exponents, right? Here, what does this mean? It means I have 8 to the power of 1/5. What does this mean? It means I have 8 to the power of 1/5. Following? So in total, how many do I have? I have 12, okay? I have 12 8 to the 1/5 powers, okay? If you wanted to convert it to radicals, that might make it easier for you to see, but it doesn't matter as long as you understand the concept, okay? All right, C. Remember what I said. In order to combine these, they have to have the same root and the same value under the radical, which in this case, I don't have that. So what I would need to do is check to see if this could be simplified further before I walk away from this problem. So are there any perfect cubes contained inside of 54? You guessed it, the answer is yes, because 54 is equivalent to 27 times 2. So I could rewrite the first term as 3 times the cube root of 2 minus the cube root of 2. So if I have 3 here and I'm subtracting 1 from it, I have 2 times the cube root of 2. Okay? Make sure when you write this, you make it clear that this is its own item and it's not connected to this, because some people write it like this. And then it's like, is this an exponent of 2 or a cube root? You know what I mean? All right, continuing on. Simplify each expression. Here, these two problems we saw in lesson 7, at the end of lesson 7. But so in this case, I'm looking for perfect cubes, okay? Now, I usually break it up into pieces, so I look at the numbers and then I look at the variables. So what number times itself 3 times gives you 64, or what number cubed gives you 64? The answer is 4. What variable multiplied by itself 6 times gives you y to the 6th? Well, that's just y squared, okay? And what you could do is divide the power by the root, because if I was to put this into exponential form, right, this would be 64y to the 6th, all to the power of 1/3. Right? And then that's 64 to the 1/3, which that's harder to understand, but y to the 6 over 3 power, that makes more sense. That's y squared. okay? Okay, moving on. I'll leave it there, actually. Okay, same idea here. I can divide the power by the root and get x to the first over y squared, which is just x over y squared. Or I could think about what quantity times itself would give me x to the fourth, x. What quantity times itself 4 times would give me y to the eighth, y squared. Very good. Let's keep going. Okay, now in this case, this is where we see how do I approach a problem where they're not perfect fourth roots or not perfect cube roots and so on. So again, just break it into pieces. I have 16. What number multiplied by itself 4 times gives me 16? 2. Okay. A to the 7th. What quantity times itself 4 times gives me a to the 7th? Well, nothing. Okay, so here's where I have to break it apart. I also know because 7 isn't divisible by 4. So just like I've seen or we've seen in previous problems, like here, where I could break it apart so that I get a perfect cube, I could do the same thing here. All I have to do is break it apart into something that is divisible by 4, okay? And you always want to get the biggest number possible. So what I do is I break a to the 7th into a to the 4th times a to the 3rd, because this is a perfect fourth root, or a quantity to the 4th power, okay? And then I can simplify that to a times the 4th root of a cubed. Okay, let's try another one, because I know might be a tricky concept. So 11 isn't divisible by 4, and no quantity times itself 4 times would give me b to the 11th. So I need to find a number close to 11 that is divisible by 4 and as large as possible. So I would break it into b to the 8th times b to the 3rd, because 8 is divisible by 4. So what I get is b squared times the 4th root of b cubed. And then the nice thing about this last one is it is divisible by 4. So that would just be c. Okay, so now I'm going to put my answer together. You don't have to do it this way. I was just trying to show you how I think about it in my head. Now I'm going to put it all together. So the final answer would be 2c a, well, actually, I'll put it in alphabetical order, because why not? 2a b squared c, so I'm just taking all the quantities outside the radical, times the 4th root of a cubed b cubed. So now I just took the ones that were left over and put them inside, okay? All right, let's try another one. All right, here, it's not a matter of taking out, although you could definitely take things out of the radical here, but it's more about rationalizing the denominator. So if you remember, in order to rationalize the denominator, I need, in this case, a perfect cube or a number cubed. Now, if you look at what's under the radical, how I think about it is I need a number that's going to divide into 3. 8 isn't divisible by 3. But what I could do is I could multiply the top and bottom by y to the first, so that in the denominator, I get 3 times the cube root of, not 3 times, I apologize, the cube root of y to the 9th power, and that is divisible by 3, I'm sorry. And then in the numerator, I have x times the cube root of just y, okay? So the denominator, after it's simplified, would be x times the cube root of y all over y cubed. And then that's the fully simplified form. Okay, this one. Here we want to simplify using exponent rules since everything's already in exponential form. Again, I kind of like divide and conquer, just look at one thing at a time. So I'm going to focus on the coefficients. So 2 goes into 14 7 times. Then I'm going to look at the x variables. So this is x to the first power. That's x cubed. Or sorry, x to the 3/4 power. So that's going to be x to the 1 minus 3/4 power. I'll finish that part afterwards. Then you have y to the 1/3. There's nothing I can do with that. And then you have z to the negative 6, so that has to get moved to the numerator, okay? So when I subtract 1 minus 3/4, what I end up getting is 7 times x to the 1/4, y to the 1/3, z to the 6th as my final answer. Okay, almost there. Last one, 8. Perform each indicated operation. Assume all variables are positive. Okay, so this is just like the previous one. I have 5 square root y's here, 6 here. So in total, I have 11 square root y, just combining like terms. Here, I have the same root, but not the same radicand, not the same number under the radical. So I should check to make sure I can simplify these further. So 2 can't be simplified further, but z to the 5th can. I would break that into 2 times z to the 3rd times z squared. So that would give me 12z times the cube root of 2z squared. Okay, move on to the other one. 54, is there a number times itself 3 times that gives me 54? No, but I can break it into the cube root of 27 times 2. And then z squared, I can't do anything with that. So this is equal to 3z times the cube root of 2z squared. Okay, now this is a unique problem because in order to combine these two terms, not only do I need the roots, the numbers under the radical to be the same, but these also have to be like terms in order for me to combine them, which they are. So now I can combine like terms, and I'm just going to get 9z times the cube root of 2z squared. And that's my final answer. And that's the end of the lesson.